Okay, so last time we talked about the L-shaped, what I argued and hopefully convinced you is that if we are getting an X that is in K2, let me remind you what K2 is. K2 is the set of X's such that I can find a second stage reaction that's feasible. So for every scenario from 1 to capital K, I can find a Y that's non-negative and that satisfies this. So, oops. Okay. Down here. Okay, there we are. So if we're always sending from the master X's that are in this K2, we generate an optimality cut, and I showed you that you can only generate finitely many optimality cuts, so the L-shaped algorithm at some point will terminate. Now, one could turn around and tell me, okay, your proof of finite termination is valid as long as you're always producing X's that are in K2. So who is to tell me that the... So I would answer back to this guy, yeah, but if X is not in K2, I'm also generating feasibility cuts. And that guy would answer back to me, okay, who's to say that the feasibility cuts are finitely many? So this is what I'm going to try and demonstrate to you today. And the easier thing to see with feasibility cuts is why they can only be finitely many. It's exactly the same argument that we use for the optimality cuts. So to generate feasibility cuts, we solve this feasibility problem that is trying to minimize the level of violation. So the V pluses and V minuses are non-negative variables that help us satisfy these constraints. How many of these problems do we need to solve at each iteration? Capital K. And we solve them sequentially. When we detect a violation, the W prime is positive. How many, and we get the sigma multipliers that we use for generating the feasibility cut. These sigma multipliers, the way simplex computes them is using the optimal basis of this problem here. There are only finitely many optimal bases of this problem, so you can only get finitely many feasibility cuts. That's the argument of why this can only happen a finite number of times. Now, the other thing I want to make sure is what I drew for you last week, which is that we have a K2, we also have a K1, and what we are interested in the intersection of these two sets. That's really the set of X's that we care about. So this space that I'm looking at here is the dimension of the first stage decisions. So the only first stage decisions I'm interested in are the ones that are in this space, but when I'm imposing a constraint like this, I'm basically defining a half space here, and there is a candidate XB that I want to cut off, and I want to make sure that this space is on the other side. So I want to now convince you that yes, the XV will be cut off. So this half space will have this XV on the other side. So once I then define this inequality, XV can never be considered again because it violates this inequality. But at the same time, I want to make sure that I don't move this line somewhere where it cuts off stuff that should be considered. That's the geometry of what I'm trying to show to you now. So there will be finitely many of these lines generated, but we don't want to cut off feasible candidates. And the way to see that is the following. So the argument that this xv is on the other side of this inequality is fairly easy, and it follows from linear programming duality. So what can you say about the sigma dual multipliers that correspond? If I tell you that w prime is a positive number, what does linear programming duality tell you? I mean strong duality. Strong duality says that dual multipliers times right hand side is equal to the objective function. So what are the dual multipliers here? The dual. Come again?
Well, the question is what represent the dual multipliers?
Not what they represent, but what does strong duality say for this problem? Strong duality is the result that says that the dual optimal multipliers of these constraints times the right-hand side of the linear program equals the w prime. So w prime equals sigma times great. But I know w prime is 0 if this turns out to be a nasty problem. So if I detect a w prime that's positive, the sigmas I get are such. Well, what's the feasibility cut I defined? Feasibility cut, this dx greater than or equal to d, the dr plus 1 was defined as this thing here. That's the recipe I gave you for computing it. And the little d was defined as this guy here. So once I define this as a new feasibility cut, could xv ever satisfy this inequality? This is the recipe for computing this cut. Question is, could xv ever satisfy this? It violates the strong duality result I just showed you. So we're setting up this inequality to kick out xv. That's the idea. We don't want it to come back. So we're good about this side of the geometry. Indeed, xv lies on the wrong side of this half space. The next thing we want to show is that all these guys here lie on the other side of this inequality. So now I've been showing you a drawing in Rn1, the space of x's, x variables. I want you to think, swap dimensions and go to Rn2, which is the space of the dual constraints. And here's what's going on there. So we're moving from Rn1 to Rn1 to Rn2. Basically, when I am considering x's that are feasible candidates here, this creates through this transformation here a set. So this intersection of k1 and k2, when I pass it through this transformation here, it creates a set in Rn2. Is that so? The transformation I'm going to do is h minus dx, and that creates another set. And I want to make sure that this set is so the xv is transformed to h minus dx v. So I just instead of looking at RM1, I'm looking at RM2. Okay, so the argument now goes as follows. This set of guys that I don't want to kick out is a subset of a bigger set called positive W, which is basically the space I can span by taking non-negatively scaled columns of W. I have a bunch of columns of W, those are in RM2. What is the space I can span? By adding these up with non-negative coefficients. This is called pos W. And I argue that this set here, transformed through this H minus Tx, is contained in pos W. The reason that's true is by the definition of K2, if you think about what I just told you. This is exactly the definition of K2. So, in particular, x's that are in K2 means that there is a y such that Wy equals H minus Tx, and the y is non-negative. So that shows that this set of eligible bachelors that I don't want to kick out of the party is contained within this bigger set post W. Okay, so now the question is, when I'm drawing this line, I'm not only going to show you that this set is on the right side of the line, but actually all of post W is on the right side of this hyperplane. And the way to show that is basically by the, you can go through the argument, it's not a difficult argument, but it just takes, when you first see it, it's kind of heavy, but it's not that bad. The argument is to exploit what is the definition of an optimal basis of the linear program over here. Do you remember what specifies an optimal basis for a linear program? Again, feasible, non-negative basic solutions and non-negative reduced costs. These are the two criteria for, this is a feasible basis, and non-negative reduced cost is this condition over here. So when I apply this for this linear program here, the A matrix of this program is the W part, and these two parts over here. So once I plug in everything, the inequality that comes out is basically this one over here. That said, so I know that for these multipliers, this inequality is satisfied because this basis is optimal. So then if I multiply both sides of this inequality by a non-negative y, I get exactly the inequality that I needed here. Okay, so again, the argument to recapitulate is the following. First of all, easy to show xv is on the wrong side. That just comes from strong duality of linear programming of the feasibility problem. Then I move from looking into Rn1 to looking into Rn2 through this transformation, and I show that the set I'm interested in is contained in post W by the definition of K2, and then I show that post W is on the right side of this hyperplane by using what characterizes an optimal basis, which is that reduced costs are greater than or equal to 0. That's the argument. Okay, I know it's heavy to digest when you first see it, but hopefully it becomes easier to deal with down the line. Okay, so the cuts are valid. They don't kick out anyone that I don't want them to kick out, and they're finitely many. Also, the optimality cuts are finitely many, so L-shaped will converge finitely. Are there any questions? It's heavy. But if there are questions, okay. So now I'll move to something more practical, which is how your solver behaves when you're implementing the algorithm. Okay. And this is a problem that Matthew encountered 3 days ago. So Matthew implemented the L-shaped method as instructed in the textbook using CVX instead of AMPL, and got optimality cuts that were off. They were wrong. So let's dig into the details of what dual optimal multipliers are in solvers. And the definition is different for different solvers, which means when you get a prescription from a textbook of how to do something, you want to make sure that prescription is compatible with your solver. Okay, that should not be in this presentation. Did I not compile? Okay, yeah, I didn't compile. Okay, maybe I forgot to. So you will not hear about dual multipliers in CVX because we're not 100% sure about how they work yet. We'll have it next year. But the important message is here. So the set of KKT, okay, what dual multipliers depend on is basically the set of the KKT conditions. When you are asking your solver what is the dual value of a certain constraint, the solver has come up with that answer by solving a set of KKT conditions. And these KKT conditions are different depending on how you define the Lagrangian function of a problem. Do you remember where the KKT conditions came from? From the duality class. What was the first thing we did when we took an optimization problem to land into the KKT conditions?
Right.
Exactly. You relax the problem, and you write. Now that there's the tricky part already. Is there any specific? So when I have an optimization problem.
Maybe decide which constraint you want to relax.
Suppose I know that any solver out there relaxes all of them to define KKT conditions. There is still some freedom, and that freedom is used differently in different solvers. So let's think of a minimization problem. What's the freedom that I have? We just define the Lagrangian as a weighted sum of the F0 and the constraints times their multipliers, but I never told you whether you're supposed to subtract or add these things. So one way you could go about it, which is what AMPL does, is subtract. This is AMPL. Another thing you could do is add, and I'm not sure this is what, I know this is what CVX does in terms of the less than or equal, because in the manual it says you always get lambda greater than or equal to 0, which you can only get if you add. But I'm not sure that's what it does with the equality constraints, which is why we removed that part of the presentation from today. But I'm going to write CVX here. I don't know what of these two things it's doing. But for the inequality part, I can tell you this is what it does. And then what happens after this is, so what we do after we define the Lagrangian is minimizing. The minimization part of the Lagrangian defines, there are four KKT conditions. At least that's the easiest way for me to remember them. One is primal feasibility, dual feasibility. And the fourth is complementary slackness. You already have dual feasibility constraints based on the way you define the Lagrangian. What are they for this problem here? What's the logic? Exactly. The way you relax the problem has to create, for a minimization problem, a lower bound. Actually, if you were maximizing, again, because you want to get a bound on a maximization, the lambda would have the opposite sign. So you're always defining the sign of the dual multiplier so that you bound in the sense of what you're doing. If you're minimizing, your Lagrangian creates a lower bound. If you're maximizing, the way you write the Lagrangian, depending on the signs you choose here, you specify the sign so that it's an upper bound. So already here, for AMPL, you already have a difference. AMPL here will ask for a lambda that is greater than or equal to 0. Yeah? Yes? No. Less than or equal to 0. So I want to be getting... Come again?
Like,
if it's less than or equal to this 0 and I have a feasible x, I get something positive here, so that's pushing this down, which is exactly what I want. Exactly the opposite in 2bx. Already, we're minimizing, so we want this to be even lower if we are feasible. So if, okay, good. Already here, I know I'm going to get different answers from the solver. And question is, which one is the book telling me to do? And I'll address that in a couple of last slides of the presentation. Let's see how much time we have. We run into we stop at 4, right? Not 4 past. Okay. Okay. Now, okay, actually this is what I really wanted to make sure you remember, and from here I can get into also the complementary slackness and so on, but really the sign is what I wanted you to get in your heads, and it seems like you're already under control of that, so we're in good shape. So I will jump to the instructions you need to remember. And I will only give you these instructions for AMPL because that's the one software I'm, from testing it, confident I know what it does. I'm not sure what CBX does. Okay, so the syntax of your constraint matters in AMPL. When you write a constraint like actually, let's think of a constraint like this. Someone could say this is a greater than or equal constraint. Why? Because the variables are on the right-hand side, so the sense of this relation is greater than or equal. That's not how AMPL will interpret this. What AMPL will do is it'll look at your syntax, see what's on the left-hand side, and it'll send everything to the left-hand side. And if you define this as a less than or equal constraint, it's a less than or equal constraint, and your fi function here is 2 minus x. Okay, if you wrote it like this, again, it looks like a greater than or equal constraint, but because you've used this syntax, according to AMPL, this is a less than or equal constraint with this fi. Okay, if you had used this constraint, then this would have been a greater than or equal.
The second one is the same.
Come again?
For the second one, it's the same fi than for the first one?
Yes. Yes. But here it's the opposite, and also it's a greater than or equal constraint, according to AMPL. Okay, so when it builds the Lagrangian function, there's a bunch of other fi's here that can be greater than or equal, according to AMPL. According to CVX, and this is I think consistent with Boyd's book, there are no greater than or equal constraints. Boyd transforms your syntax always in a way that you get less than or equal constraints, but AMPL doesn't do that. So for AMPL, I'm gonna write F1ix and F2ix for greater than or equal. And I have lambda 1s and lambda 2s here on the slides. Okay. And so that's the first thing AMPL does looking at your syntax. Then it always builds a Lagrangian like this for both types of constraints, greater than or equal and less than or equal. So here, the way it builds the Lagrangian is F1i. And also the same for the greater than or equal constraints. The reason it does this is practical. From the vanishing gradient condition of the KKT conditions, you have the following relationship. You have basically the reason AMPL does this, the reason it subtracts the scaled constraints is it wants to report sensitivities at the output. If you write the vanishing gradient condition here, you get this. And this has to be equal to 0. So when you move all of this stuff to the right-hand side, the sensitivity of an increase, for example, in the right-hand side of F1 is exactly the marginal change of F0. It's not minus the marginal change. Whereas Boyd, writing the Lagrangian like this, reports a number when you're asking for dual multiplier, but actually that's minus the sensitivity of a problem. So when you would have, for example, a linear programming minimization, what would you expect from linear programming textbooks to be the sensitivity of a constraint like this? What sign would you expect it to be based on what you know from thinking in terms of sensitivity? Positive or negative?
Negative.
If you have a bit of more of a feasibility. AMPL will tell you negative. Boyd will tell you, not Boyd, CVX will tell you positive. Okay. And that's a practical reason that AMPL, I think, I haven't talked with them, but I think that the reason they define Lagrangian like this for any type of problem, either minimization or maximization, is so that they can report sensitivities. Okay, so that's that. The sign of the dual multiplier is such that the Lagrangian function provides a bound. And then the primal dual optimal pair is such that the KKT conditions are satisfied. And in this way, AMPL reports sensitivities. So what I just said is formally described here. I have F1 type of constraints for less than or equal, F2 for greater than or equal. This is the Lagrangian function that I wrote over here. And then here's how you get, and you've seen this slide before in the duality part of the second lecture. This is how we get basically complementary slackness. This is the argument we use to get complementary slackness and vanishing gradient. But the important thing that you've already understood is the logic of creating a Lagrangian function. That's really what I want you to remember. Okay. And here's an example of how that works specifically. Minimize x plus 2y subject to these three constraints here. based on what I've told you already, you will get this Lagrangian for the following reason. The objective function remains the same. This constraint is transformed to, we shift everything to the left and maintain the sense of inequality. So this is a minus x constraint. This becomes x minus 2, and this becomes y minus 1. Again, we're shifting everything to the left. And we're then subtracting all of these constraints in the Lagrangian function description. Clear? Now, the KKTs of this problem are here. So I can write them out specifically for this problem. But if you go and look at them, you will convince yourself that this is the solution. And there is sensitivity content in these multipliers. So y is lambda 2, 0, for example, for this. What's the optimal solution of this problem? Optimal solution. 0, 1. Right. So what's the sensitivity with respect to this guy? 0. Doesn't matter. But here, how much for this constraint?
What?
Which? Why? Here's the cookbook argument is increasing right-hand side, good news, so it must be negative, and then it contributes 1 to the objective function. So I know it's negative, and I know its magnitude is 1, so it's minus 1. But you can return to the KKTs and look at them carefully and confirm. Okay. Now, how does all of this come into play for the L-shaped algorithm? Well, it turns out that the textbook had in mind what you know in terms of AMPL, not what is described in Boyd's textbook or what's implemented in CVX. So this is generically the problem you will be coding for the L-shaped algorithm for the second stage. And by the way, I'm not sure if Matthew covered this already or if it's going to be in the next training section, but the same recipe that you're given in the book, you can apply it for a more general description of the second stage. You don't have to have equality constraints in the second stage. You can have greater than or equal and less than or equal constraints. It's just that you have to store them in different multipliers. So the 1, 2, and 3 indexes here are indicating equal, greater than or equal, and less than or equal. Yeah.
Actually, it's kind of like question 2 of this session. So to do that, you can write on your own notation.
Okay. So the crucial thing for the L-shaped algorithm to work is that this optimality cut yes. I'll do it from the slide. In the L-shaped algorithm, you compute an optimality cut, and the recipe is this one. It's ES plus 1, little e minus the coefficient S plus 1 XV. And this is a hyperplane. You want it, when you evaluate it at XV, to equal the objective function of the second stage problem. Not minus that or anything else. You want that cut geometrically to exactly support your value function. If this is your value function at XV, you want this line to exactly support it. So basically, this is what your from linear programming duality for the second stage problem, you know this holds. So the optimal solution of this problem, which we denote as Q of xv for scenario K, is, the right hand, the dual multipliers times the right hand constraint. So that's where this equality is coming from. And we know from the KKT conditions that I showed you earlier, for AMPL specifically, that this condition holds. For CVX, it would be plus, plus, plus. If it were plus, 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 that wouldn't be good for us, because then if we multiply everything here with y star, the optimal, the second stage optimal solution, if it were plus, 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 then Q would be minus the optimality cut, not the optimality cut. So you're going to get very bad stuff happening. Basically, instead of generating this, you're going to generate something like this. Okay. That's basically what I wanted to share with you today. And is there any questions with this? Are we good? Just, keep that in mind. It's different solver. If you try and experiment with a different solver, make sure you understand how it generates primal dual KKT system, because that will make a world of a difference. And it's not only the L-shaped method that uses dual multipliers. You have Danzig-Wolf that uses dual multipliers. There's a ton of algorithms that exploit dual information. And if you don't understand the dual information, also in economic modeling, you have a problem. If you don't know if you're getting sensitivity or minus sensitivity, you can screw up the results you're reporting. So this is useful to remember for solvers.